Neural networks are a subset of machine learning. They consist of interconnected nodes or neurons that collectively work to recognize patterns in data. Central to their functionality are weights and biases. Weights determine the connection strength between neurons, influencing how signals are transmitted throughout the network. Adjusting weights impacts how the network processes input data and affects the final output. Biases facilitate neuron activation. They shift the activation function, altering the threshold needed for a neuron to fire, even under low or absent input conditions. This interplay of weights and biases, continually fine-tuned during training, enables neural networks to adapt and execute complex tasks such as image recognition and natural language processing. Understanding the synergistic roles of weights and biases is crucial in comprehending how neural networks model complex patterns and learn from data. The core mechanism by which weights and biases operate in neural networks is forward propagation. This is the process of input data flowing through the network layer by layer to generate an output. As inputs enter the first layer, the weights modify the strength of signals between neurons. Biases then shift the activation function of each neuron. These neurons send output to the next layer, where this process repeats. Appropriate weighting focuses the network on key input features. Biases ensure neurons activate even with weak input. The combined effect enables neural networks to model complex nonlinear relationships as data flows through successive transformations from input to output. Understanding forward propagation provides the foundation to explore how neural networks train and optimize their parameters through backpropagation. The core training mechanism for neural networks is backpropagation. This iterative process adjusts weights and biases to minimize the difference between the network's predictions and the true target outputs. First, input data is propagated forward through the network to make initial predictions. The error between these predictions and the targets is calculated using a loss function. This error is then propagated backwards to determine the contribution of each weight and bias. The gradients of the loss function are computed with respect to every parameter. Weights and biases are then adjusted to reduce the loss. This cycle repeats as parameters are tuned until network accuracy improves. Backpropagation enables neural networks to learn complex patterns and relationships within training data. The optimized weights and biases adapt the network to accurately model the desired input-output mapping. With an understanding of how networks train, we can now explore real-world optimization and applications of neural networks. The training process enables weights and biases to be optimized for specific applications. This fine-tuning is key for real-world deployment of neural networks. Optimization is an iterative process where the model's parameters such as weights and biases are adjusted to minimize errors. This process optimizes accuracy and efficiency by repeated cycles of update followed by training. While optimized models can power diverse AI applications, some of the most common models are feed-forward neural networks, convolutional neural networks, transformer neural networks, and generative adversarial networks. All four use weights and biases differently. Feed-forward neural networks use weights and biases to learn input-output relationships. Weights determine signal strength between neurons and focus on relevant input features. Biases in feed-forward networks shift neuron activation thresholds, enabling activation with weak inputs and capturing complex patterns, enhancing learning in various domains like image and language processing. In contrast, convolutional networks use shared weights in convolutional filters for spatial pattern identification in data, reducing parameters compared to feed-forward networks. Biases adjust outputs from convolutional layers and play a significant role in fully connected layers for classification enhancement. These specialized roles make convolutional networks adept at image and spatial pattern tasks. Transformer networks use selective weights and attention mechanisms to focus on important parts of input sequences, capturing long-range data dependencies. Biases integrated into feed-forward networks within encoder-decoder blocks fine-tune attention outputs, making transformers effective in sequential data processing and language tasks. Generative adversarial networks use two networks, a generator and a discriminator, that train adversarially. The generator's weights learn to mimic real data distribution, creating realistic samples. The discriminator distinguishes real from fake data using weights. Biases in both networks enhance sample diversity and detection accuracy. This adversarial training enables generative adversarial networks to generate novel synthetic data with high realism, distinguishing them from other generative models. So there you have it, an introduction to weights and biases in neural networks, based on the video, I would suggest the following takeaways. 1. Weights and biases are used to fine-tune input data such that neural networks can learn to recognize complex patterns and perform tasks such as image recognition and natural language processing. 2. Forward propagation and backpropagation are the two fundamental processes that govern the operation of neural networks. 3. Neural networks have a wide range of real-world applications, from image classification and speech recognition to language modeling and generating creative content. I sincerely hope that you found this video to be informative and worth your investment of time. If you have not already done so, see our other videos on neural networks. Also, be on the lookout for a video discussing forward propagation and backpropagation in detail. Until next time, thanks for watching.